There is a creature in the ocean that punches with the force of a bullet. The impact is so violent, it boils the water around it, creates a flash of light, generates temperatures rivaling the surface of the sun. This animal has shattered aquarium glass designed to contain sharks, broken through crab shells in a single strike, severed human fingers. It measures 15 centimeters long. This is the mantis shrimp, and everything about it violates the laws of physics and biology. Its eyes are more complex than any camera ever built. Its punch is faster than a snake can strike. Its body contains materials that shouldn't exist in nature, and we have no complete explanation for any of it. Mantis shrimp have existed for 400 million years, longer than trees, longer than sharks in their modern form. Over 450 species live in tropical coral reefs worldwide, but the true extent of their capabilities remained hidden until the 1970s. When researchers finally studied their hunting mechanics, they discovered something impossible. The mantis shrimp was a biological weapon system operating at the absolute limits of what organic matter can withstand. There are two types. Spearers have barbed appendages for impaling soft prey. Smashers have club-like appendages for crushing hard shells. It is the smashers that defy explanation. They live in burrows. They are territorial, aggressive, and capable of recognizing individual rivals. But these basic facts reveal nothing about the impossible biology underneath. The mantis shrimp's punch accelerates at over 10,000 g-forces. The club reaches 50 miles per hour in under 3 milliseconds. A professional boxer's punch generates 50 g-forces. The mantis shrimp generates 200 times more. From an arm smaller than your finger, accelerations above a few hundred g-forces tear muscle, shatter bones. The mantis shrimp does this thousands of times without injury. Muscle alone cannot generate this speed. The mantis shrimp evolved a biological spring system. A saddle-shaped structure compresses slowly, like a crossbow. A latch holds it, then releases. The spring unfolds in 3 milliseconds, transferring all energy instantly. Each component operates at the limits of material strength. The strike is so fast, it weaponizes physics itself. As the club moves through water, it creates a low-pressure void. Vapor bubbles form, cavitation. When these bubbles collapse, they release shockwaves. Temperatures briefly reach thousands of degrees. The prey is hit twice, first by the club, then by the shockwave. This is cavitation, a phenomenon that destroys ship propellers. The mantis shrimp weaponized it. The only biological system on Earth that does this deliberately. Humans have 3 types of color receptors. The mantis shrimp has 16 types of photoreceptors. But behavioral studies reveal something baffling. Mantis shrimp are worse at distinguishing colors than humans. Why evolve 16 receptor types for inferior color vision? Then there's polarization vision. They can detect the orientation of light waves, something humans need specialized equipment to measure. The biological function remains unknown. The club must survive impacts that would shatter bone. Thousands of strikes across the organism's lifetime. The structure is a composite material, more sophisticated than modern engineering. The outer layer contains mineralized chitin with crystalline calcium phosphate. Beneath it, chitin fibers arrange in a helical pattern, a bouligand arrangement. This exact structure is used in aerospace composite materials. The mantis shrimp evolved it 400 million years ago. Materials scientists are now copying this design for body armor. Generating a 10,000 g-force strike in 3 milliseconds creates an impossible problem. Standard neural processing takes 50 to 100 milliseconds, far too slow. The solution is semi-autonomous release. Once triggered, The strike proceeds mechanically, no adjustment possible. Yet they hit moving targets with remarkable accuracy. This requires pre-strike calculations from a brain the size of a grain of rice. We do not understand how this is possible. This requires pre-strike calculations from a brain the size of a grain of rice. We do not understand how this is possible. Instead of comparing signals between photoreceptors like humans, Mantis shrimp use parallel processing. Each receptor responds to a narrow wavelength. The brain processes these separately. This is faster but less precise. One hypothesis: the visual system is for communication, not perception. Mantis shrimp have body parts that reflect polarized light in patterns invisible to predators but visible to other mantis shrimp. Covert signaling, territorial displays, mate recognition, all hidden from other species, but we cannot decode the information. The mantis shrimp's extremes may result from evolutionary arms races with armored prey. Stronger prey defenses select for more powerful strikes. More powerful strikes select for stronger defenses. The cycle escalates across evolutionary time. The mantis shrimp may represent the apex, the most powerful biological strike mechanism physically possible. But why hasn't this evolved elsewhere? Perhaps all factors had to align perfectly. The spring mechanism, the material science, the neural control. Evolution found the solution once, and only once. Documentation triggered research across multiple fields: biomechanics, materials science, vision science. But mantis shrimp are extraordinarily difficult to study. They destroy laboratory equipment. High-speed cameras were essential to capture the strike. Specialized optical equipment to measure polarization. Public aquariums learned that standard acrylic walls cannot withstand their strikes. Larger specimens shatter viewing panels. Solutions involve reinforced acrylic or isolation tanks, engineering for large, dangerous vertebrates. For a 15-centimeter crustacean, research has yielded practical applications. The Bouligon structure now informs body armor design and impact-resistant materials for vehicles. The visual system inspired camera sensors detecting polarization for autonomous vehicles and medical imaging. The spring mechanism informed prosthetic and robotic designs. Products incorporating mantis shrimp designs are in active development. Why did 16 photoreceptor types evolve? How do they control strikes faster than neural signals can travel? What is the maximum striking power achievable biologically? Why hasn't this evolved in other predators? The mantis shrimp was known for over a century before its capabilities were documented. What other organisms possess capabilities we haven't measured? Is the mantis shrimp optimally adapted or over-adapted? The 10,000 G-force strike seems excessive for breaking shells. The 16 photoreceptors seem excessive for color recognition. Yet these capabilities persist across millions of years. Perhaps we misunderstand selective pressures in coral reefs, or perhaps evolution sometimes achieves the absolute limits of biological possibility. The mantis shrimp may represent that ceiling, the fastest, most powerful biological strike that can exist. 400 million years of refinement to reach the absolute maximum. The mantis shrimp possesses capabilities that violate our understanding of biological constraints. Forces comparable to ballistics. Vision more complex than any organism. Materials rivaling engineered composites. But another creature has achieved something even more impossible. This microscopic organism survives complete desiccation. Temperatures near absolute zero, the vacuum of space, radiation thousands of times beyond lethal doses, the tardigrade, the most indestructible organism ever documented. And we have no theory explaining how.